Yago Rocha recibió el grado de licenciatura con summa cum laude en Ingeniería Eléctrica de la Universidad Federal de Río Grande do Norte en Brasil en 2016. En 2018 obtuvo el grado de maestría en Sistemas de Control por la Universidad de Campiñas, Brasil también. Obtuvo su doctorado por la Universidad de París-Saclay en 2021. En 2022 fue investigador postdoctoral en el Instituto Francés INRIA. Se unió al equipo de investigación de asistencia a la conducción de Valeo Francia en 2023. Su interés de investigación incluye sistemas de pelotón, aprendizaje por refuerzo e interacción de control y comunicación. Thank you for joining us today. We are ready to listen to your presentation.
Your audio is closed.
Hello, can you hear me now?
Yes.
Okay, thanks. I said thanks for this kind presentation, and I'm very glad to be presenting to you guys today. Unfortunately, my Spanish is not so good to make this type of presentation, so I will speak in English, but don't hesitate. I understand very well in Spanish. Let me, you guys can see my screen. Let's just make sure you guys can see everything.
Yes.
Okay, so I'll put it here and I'll put in full screen mode. Okay, so I'll be so my talk today is about deep reinforcement learning for autonomous driving systems, because of course it's the topic I've been studying for quite some time. And this is a few presentation about myself. You guys already did a very good one, but it's just to mention, yes, I'm a software engineer at Valeo, which is a French company that makes softwares and also some sensors for cars. And I did also a postdoc in decision-making trajectory plannings for automated driving systems in INRIA, and a PhD thesis in France, also a master in control theory in Brazil, and an electrical engineering degree. So the outline of this presentation today, I would like to bring and I will be focused on automated driving systems. So I'll be introducing a bit about automated driving, or what are the main points regarding that, and then I'll be diving in some reinforcement learning techniques and some main concepts. Then I will discuss briefly why you can see the deep term in deep reinforcement learning, why people use this deep word. And then I will be discussing about two publications. One I did on my PhD, and the other one on my postdoc. So everything related to reinforcement learning as well. And finally, I'll be discussing some current and future deep reinforcement learning applications. So to start with, on this introduction for automated driving, I would like to mention that actually a car needs to see the world, and how this is done is done through the bench range of sensors. It means, for instance, you can have some cameras in the car, you can have some lidars, you can have some radars that will be able to sense, to see the world, and then this information will be used in the computer in the car to make an action. So, for instance, Valeo, it's a French company, as I said. We also make a lot of different sensors, and we sell to other companies. And I work as a software engineer, so I am trying to write some code and to be tested in the car. So actually, once you have these sensors, the next point is, what are actually autonomous cars, right? When you think about autonomous cars, the first thing it takes in your mind is actually the fact you think the car is 100% autonomous and can do everything by himself. But actually, when you work in this sector, there are actually 6 levels so the car can be autonomous. And actually, the one you think of when the car is autonomous, the last one is called full automation. Is actually when you don't need at all a driver, and this can actually be the case. There's no car actually today that is level 5, which means it's not possible yet. And I don't think, to be honest, as long as I'll be alive, I will say this is so difficult. So there are also other levels. I'll go very quickly through all of them. So the level 4, the difference between 4 and 5 is that actually level 4 is example of the Google car, for instance. There are some robot taxis. They don't need a driver, it's true, but they just work in specific city or in specific neighborhood of a city. In US, for instance, you can find those. But if you put that car in Paris, for instance, it is not going to work, because that would be like level 5 car that would work autonomously everywhere in the world. And this is not possible yet. So the level 3 difference is called conditional automation. And the difference that actually the driver can have some eyes off in some situations. So the car is taking the whole decision in some situations, okay? And then level 2 is called partial automation. It's when the car is actually steering for you, the wheel, and accelerating or braking the car. So it makes both of them. But you have to keep eyes on the road, okay? And then we have driver assistance is level 1. It means the car is able to either make this longitudinal acceleration or braking the car, or steering the wheel, one or the other, not both, okay? And finally, we have no automation at all. It's actually when you have some just warning systems that is not controlling the cars, not doing anything, but just saying, okay, show some images and some signals noise to the driver to warn the driver, okay? And I have actually, so the point is, when you think about autonomous cars, there are actually functionalities. So you click some button in the car, and then for a specific moment, the car will be level 1, 2, 3, or 4, or 5, okay? So we have different functionalities. I'm not going through all of them now. I brought some quick quiz. I will give you, so the point is there's one functionality, for instance, called ACC, it's called Adaptive Cruise Control. And the point is the car is able to detect the car in the front and accelerate and brake. That's all you can do. The car is not steering the wheels, not doing anything else. So I'd like to just give you a couple of seconds to think what type of autonomous vehicle this type of feature it is. So yeah, I'll give just a couple of seconds, but the answer is level 1. Yes, because the car is just actually able to accelerate or brake the car. So that is a functionality you can see some today, and it's level 1. I brought another one, which is called blind spot monitoring. So it's when there's some cars behind your car and you cannot see through this mirror on the left. So this feature is gonna beep some sound here or some lights here on the mirror to say, okay, be careful, there are some cars behind you that you cannot see. So also this is a functionality, and the quick quiz is to try to guess which level this is. I'll give a couple of seconds. I'm not sure you guys can talk, but I might proceed there. So the answer is level 0, because again, this is not actually not controlling the car. It's just so warnings for the driver, okay? And finally, I have last one example is called a traffic jam chauffeur. So it's when actually in this situation, the car, through this range of sensors, detects all the objects in a traffic jam when there are a lot of cars in this jam in a city, for instance. So there's a low speed situation, and the car is actually can turn the wheel and accelerate and brake and do everything, but just for a specific time, the driver is not driving. So yeah, for this specific case, the answer is level 3, because for a specific moment, the driver is not driving the car. He can do something else, like check his phone or something. But that only works, again, in this specific crowded situation with a lot of cars, okay? So I would like just to mention that there are only 2 manufacturers companies in the world today that have level 3 cars. So when you think about Tesla, Tesla is actually level 2. Tesla is not level 3. You might know a lot about this car, but the only 2 companies that can sell level 3 cars certified are Honda and Mercedes. So those are the top companies that say most autonomous cars in the market. Of course, I'm not talking about robo-taxis, right? Like Waymo and so on, that, yeah, they are level 4 in some specific neighborhood in US or city in US. Okay, so once we've done like this little introduction and quick about automated driving, you see there are many different levels of automated driving. And I'll be diving now how you can use reinforcement learning now with automated driving, okay? So the first point is, what are actually the difference between reinforcement learning and the other machine learning paradigms, okay? As you can see on this picture, reinforcement learning is just one branch of the machine learning paradigms. So the actually difference is that, for instance, unsupervised learning, you have no label, so you are able to do clustering. It means you can separate some data and clusterize them. The other ones are, it's called other learning paradigm, is called supervised learning. This one you have some sort of label, and it says, okay, you can classify, okay, this is this data is this point and this is this point. This is, for instance, used for image when you want to know, for instance, if there's a cat or a dog in the image. So you can classify. The third one is called reinforcement learning. Is the one you're going to focus today, and is actually used for decision making. So different from the other ones, this one here, you need some sort of iterations, and it doesn't rely actually on static data. Those two paradigms, you require a lot of data. So what we call usually data sets, which is statistics data. So you take images, you take a lot of points, and then you want to try to learn something through this data. In reinforcement learning, is not the case, okay? You don't need a lot of data before. You're actually going to create a lot of data later. But the point is, in reinforcement learning, you need some sort of simulator. Is actually done, is actually a learning paradigm that needs that solves decision-making problems, and through actually trial and error iterations, okay? So I will try to explain in a brief way, in a simple, let's say, car scenario like this one, the main points of reinforcement learning before I give some more details. So actually the main points of reinforcement learning, you have to keep in mind, you need some agent. That means you need some algorithm, you need some taking an action, okay? So I have an agent, which is actually an algorithm that is gonna take an action, okay? So, and in this action, let's think about this car as being this agent. So a smart car that's gonna is trying to learn something. And then this car is gonna make an action in an environment, okay? And what is an environment? You can also see an environment as the simulator, okay? So always think when you relate the word reinforcement learning to simulator, you need some sort of simulation to be able to use reinforcement learning, okay? Either you'll be creating your own, or you need one, because it's through actually an experiment. So with this loop, they're able to implement your reinforcement learning techniques. So in this case, the environment would be this, let's say this block here, this grid, where the car cannot go out of these lanes. And let's, for instance, the objective to arrive here as fast as possible, okay? So what is actually reinforcement learning is the idea that the algorithm is going to take an action. And for instance, what are the possible actions in this is simple example are those here. You can go up, left, right, or down, okay? So the whole point is that the agent is going to take an action, for instance, going up. So you take an action, go up. You are up now, but why you are here? Actually, because when you did an action to go up, the environment is going to send back to the agent where you'll be in the next step. So this is the idea of the environment, of the simulator. You need to know what will happen if you go up. So the environment say, okay, now you are here, now you are here. So it will send this information to the agent. You are in a new state, what we call actually. So this is a new point on the grid, and we'll give some rewards. Rewards you can see as a signal that's guiding, that's able to guide this algorithm to find some objective. I'll be explaining more details, but the whole point is keep in mind, reinforcement learning is learning through experiment. So you'll be able now, the agent will do some action, we'll go to here, take an action to right, the environment will say, okay, now you're in this step of your 1-1 on this grid. So, and then so on until you arrive at some point and you have each step you have a reward. And that's more or less the basic points of reinforcement learning, okay? And how this actually is possible. Actually, reinforcement learning it's formalized always as a discrete time stochastic process called Markov decision process. So Markov decision process are stochastic process, so random possibilities and probabilities that this algorithm can take decisions, right? So the whole point is that you have an agent take an action. This environment will say, okay, your next step is here. So that your car moved to another step and you got some sort of reward that said, that's guiding this agent. Okay, you did something good, or no, you crash your car. So this is a very negative, bad signal. So this is how reinforcement learning is working. So now the agent knows, okay, I did something very bad with that action because I crashed my car. It was a very bad reward. So this is actually with this through this loop, in many thousands of iterations, the agent learns over time what are the best actions to take to solve a specific problem. Okay, and this is actually how possible because there's a mathematical framework called, as I just said, MDP, that models the sequential decision making. Is a decision making problem. Is okay, you need to take a decision now in the next step, Okay, so keep in mind that this MDP is always something you're gonna see with reinforcement learning. And what actually I brought two definitions that are very important in this for a Markov decision process. The first one is that this MDP is Markovian if actually what it means that actually the future of the process only depends on the current state and not in the full history. In some words, it just says that the probability that you go to this next state, so the car selects the car. So for instance, if I bring back, if the car was here, you want to go to the next step to go up, this probability is actually just based on where you are. You don't need the full history of your past. This is pretty much what's saying this definition number one. So you just need where you are to solve this problem. And the second definition is that the IMDP is a tuple. So it's a sequence order of parameters. So once you have the state, the action, this probability to go to a next step, and this reward, so how much good or bad you are doing at each step, you need all of those to define IMDP. Okay, I brought some, let's say, kind of complicated definitions here, 1 and 2. Let's try to understand those definitions with the example I just made a couple slides before. So the first one is that actually the fact you have the definition number 1 that say this Markov is that actually you just need the actual state. So the car is here. You just need to know where the car is to take this decision to go to the next step. Okay, that's why it says is the definition number 1. But actually, mathematically speaking, it helps a lot. That's why it's important to always mention these strong definitions of reinforcement learning and MDPs. They are very tight related, right? And the second one is that actually the MDP is a tuple, as I said. So you need the state, the action, the PR. Once you have that, you know how to solve and how it relates. Again, so what is the state? The state is actually what the car is observing in this environment. So in this case, the state is just the position of the car in this grid. So the state would be 0, 0. Okay, so you have this information. Now you need the actions, right? You have 4 different actions. So in this case, I simulated equal probability that I have 1 quarter to go to up, 1 quarter to go right, 1 quarter to go down, and 1 quarter to go left. So it means that actually when you're here, the car is able to move to here, 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 or here. Okay, so it's actually what it's saying. And those 2 are in gray because actually if you move that, the car crashes. And that means that you have a very negative reward. So you have some signal saying, okay, you did something bad, you crashed the car, and the game ends. So the episode finished, and you have to restart your game because you crash your car. So then you can see, for instance, to arrive to this specific point, the car, you have to take two decisions, either go up or right, and then it will go through a lot of iterations, and then it can find the 15. So the whole point is this is how you define MDP. Once you have all of this information, you are able to solve a reinforcement learning problem with algorithms. So the next step is actually something very important, which is this reward signal called reward, that it's actually a signal that it's able to guide your reinforcement learning algorithm. So for instance, here, when your car was here, you took an action to go left, you crash your car, you got some very bad reward signal saying, okay, you got -10 instead of just -1. So you see it's very bad. And this is actually saying and trying to guide your car to not do that anymore. So the algorithm is going to learn, okay, I don't want to have this very bad number here. I will go to up or right, so I have just a -1 reward. So the whole point of reinforcement learning is that actually you're going to accumulate at each step a reward signal until you arrive in your destination and you finish the game. So the whole point is you want to maximize this total amount of rewards, right? You want to model your reinforcement learning problem that you're able to maximize this total amount of reward. This is also usually also called the return, the discounted return, which is given by this equation, which is mean, okay, you are in step t+1, you got a reward, and then step t+2, you have a gamma times a reward, and then a gamma square reward. So the point of this gamma is actually just a parameter that is penalizing rewards in the end of your simulation. So you want to give more importance for your closest rewards, because anyway, you don't want your game to go too far away and you not sure if your actions are good or not. So you have this parameter gamma, which is a discount factor, usually around 0.9. Okay. So you have also another important function in reinforcement learning called policy. And policy is just a function that says, okay, when you are in a certain state, what action you should do. So this is just a function that maps if you're in a certain state, what you should do. So I have an example to explain what a policy is. It is often given by Pi. And for instance, if you have a random policy in this on this specific environment, it means when no matter where you are, you can go anywhere because it's random. You don't know what's the best idea. This is actually often on the beginning of your reinforcement learning problems, because the algorithm doesn't know the best choice to take. It has to iterate and many times to this loop until it learns this optimal policy. So the optimal policy means, okay, if the car starts in state here, as our goal is to arrive in this green state in as fast as possible, your action would be right. Same to here, same to here. So those are actually called optimal policy, because it means through some iteration, if you are in a certain state, it says what action you should take. So yeah, it's something very interesting and very important in reinforcement learning. It's called this policy. And the other point are value functions. Value functions, they provide information about the objective of your problem, and they help you to understand how good or bad your actions are in terms of expected future return. So in terms of this discounted return here, because once you maximize this accumulated reward, the best is your actions. So you are finding some optimal solutions for a problem. So again, here you have mainly two different functions on reinforcement learning called V function and the Q function. The V function is just saying, okay, it's how good or bad a specific state S it is when you're following a specific policy in terms of the future reward, okay? So in other words, it's just saying, okay, it's a function that is gonna do, okay, if your policies do something random, the pi, this function will say, on average, how much you can get on reward doing some crazy stuff, following some pi. So if you're here, for instance, on the beginning, it could be here, it could be anywhere in this grid, but let's say here, it says, okay, if you're here and you do a random policy, so like here, the average reward you arrive until you arrive here is this value function, okay? And the difference, you have also the Q function, which says it evaluates how good or bad your state action pair is. So it means, okay, if you are here and you're taking action to go up, how much would be your rewards until you arrive on the destination? So it's trying to evaluate this pair, and those are very important functions on reinforcement learning as well. And one natural question would be, you guys could ask, okay, but what this algorithm should learn, right? Because I mentioned about these value functions, I mentioned about the policy, but actually it depends on which algorithm you're gonna choose on a problem. And each problem, it might change. So right now you have like you can find on literature many different reinforcement learning algorithms that they rely on 3 different primary functions. So it means that reinforcement learning is trying to learn either one of these 3 functions, or sometimes 2 at the same time, as you can see, or 3 anyway. Those overlap functions here. So the 3 primary functions are first are the policy. So as I said, the algorithm is trying to find, okay, if you are in a certain state position on the grid, which one is the best action to do? So this is directly the policy. You're trying to learn based on a state what is the action you should take. Okay, so this is those reinforcement PPO. There's also some algorithms here. The other function is called value functions. I just said you can try to learn, because by doing that you're trying to on the expectation you're computing the maximize reward that you can find on your problem. So it's something that is very important and interesting. So it's called value-based reinforcement learning algorithms, for instance, Q-learning, DQ learning, etc. And there's also a third primary function to learn, which is called the environment. So it's trying to learn how actually this environment, this whole grid works, because in the beginning it doesn't know anything about it. Those are, let's say, prohibited actions. You can crash the car, you can do something you don't know. So it's something that some reinforcement learning algorithms are also able to learn. But yeah, it's a tough question. You always depend if the algorithm can be more sample efficient, and it depends really on your problem, the one you have to choose. But anyway, you have a lot of options today, and that's just to give you some broad ideas about them. Okay, so after I mentioned those points of very interesting functions to be learning in reinforcement learning, I would like to mention how this actually example of this grid links to, again, to this definition of Markovian decision process for that actually, again, it's a mathematical tool that enables to solve this reinforcement learning problem. So what are the links between them? The first one is that actually, so the action here on this, again, on this figure, the action would be, in our case, go up, right, down, or left. So we have the action A, okay? The state here would be the position of the car in this grid, because of course, if you wanna go as fast as possible to one place on this grid to another one, you need to know, you need to observe where this car it is on the grid. So it's something that you need to inform and use to give to the agent. And then you have the environment. Again, it will always think about the environment as something as a simulator. So in this case, it's a simple driving simulator that would say, okay, you are here, you took an action to go up, you are in this square here. So this is the objective, the function of the environment. Is going to say next step after an action, you went to a new state, you moved, and you get a reward, right? You go to here, so you didn't crash, so you got some 0 reward or some positive reward. Okay, And again, reward is this driving score after taking an action. So it's something is going to guide your reinforcement learning. And you have this agent with this some algorithm that that is trying to learn the best action to take. So after seeing some brief definitions and points about some reinforcement learning topics, I'd like to mention this question, which is why deep in this deep reinforcement learning term. You can always, you quite often see this on literature. So the main points about this is that actually so far we have seen and have used a very simple simulator, right? That the car moves in just this small grid and it crashes just when it hits this border, etc. So we have just 4 actions and we have 16 states. So each one of these square is a new position for the car. But actually, to be honest, this is a very simple simple case. We all know this is not the case for reality. We actually need a realistic simulator to be able to really use this, solve this problem in a real world. So for us today, because the world is not a square like this, of course. So we need some realistic simulator, okay? And this realistic simulator, let's say you have some sort of, so this is a photo from a simulator that I have worked. And you can see there are much more information. There are, let's say, more realistic buildings. You have lanes. You have traffic lights. You have a lot of information, okay, on this realistic simulator. And this actually models very well the car. It means, okay, if you go accelerate, it is somehow similar to real world car. So you have, in this case, a high dimension state and action space, because now you have much more than 4 actions and much more than 16 positions, let's say, on this using this realistic simulator, okay? And it can get worse, right? If you not deploy this reinforcement learning in a real world, you have even more like high problems in the terms of complexity to transfer this in a real world. Because of course, even though this is realistic, it's not real, it's not exactly perfect. So yeah, you have an increase of complexity. And to answer the question that I first asked, why is deep and why is related to all of this, is that actually we need neural networks to handle this high dimension input. So to handle the fact that you had many actions that are possible to be taken, you need neural networks for that, okay? So that's the answer when you think about deep in this term. So the fact that you have this term deep, it means that you're using more than 2 neural network layers for your algorithm. Because I didn't mention, but anyway, reinforcement learning, there are algorithms that you don't need neural networks. They are able to solve simple problems, but you don't need a neural network. You can solve reinforcement learning using, for instance, Q-learning with some sort of table, and you know what action you should take. But if you have a very complex problem, like a huge number of actions that can be taken, you cannot create this table. This table would be huge, so you cannot compute all the possible options that you'd have. You will need some neural networks that is gonna approximate all of those points in this table, because it's somehow infinite. It can be so big. So that's the whole point of using neural networks, and that's why we have this term deep in reinforcement learning. Okay. So after mentioning about those topics of reinforcement learning and deep reinforcement learning, I'd like to dive in a little bit in some publications that I have done in my past 3-4 years as a researcher. So the first one, as I mentioned, was related to my PhD thesis. So it's actually a problem where we have, it's called full efficient switching control for platooning systems with, again, deep reinforcement learning. And the whole point is that actually, instead of position between the cars, we are trying to maximize the fuel consumption, okay? So that's why it's called fuel efficient. And also switching control is because actually the whole point of the deep reinforcement learning is switch 2 different controllers. I'm gonna be discussing soon. for a specific situation called platooning systems. Okay, so again, to start with, we start with what are platooning systems. So these actually are the main topic of my thesis. I work on platooning systems, and what are they? Actually, are very simple. As you can see here on the left, this is actually a real platooning situation. It means when you have a coordinated number of vehicles, trucks actually, following one another in a specific itinerary between a city to another one. So the whole point is that actually companies that they want to send their goods, they can actually put a big number of trucks following one another because they have the same itinerary. And the fact that you put one truck close to another one, you have some sort of benefit related in terms of fuel consumption. And that's because when you put two trucks very close to one another, you create some sort of vacuum between the trucks. Okay, so when you create this vacuum, it means that when the first truck is going on left direction, it means that the air is touching here but not here, because this is a vacuum. So the air, instead of going here and stopping this car, the air goes here and up. So the advantage in terms of fuel consumption, it's huge for those trucks on the back. So that's actually the main benefit of doing this sort of configuration in a road. This is just to mention how I have modeled the forces that are acting in the truck. Not be discussing all of them, but anyway, just some controllers, some how we modeled the dynamics of the car, etc. So I'm not gonna go into details of this. We can discuss if you guys have some question. And the fuel consumption model is something very important because it says, okay, how is the actually in the impact of certain parameters for the fuel consumption, right? Because we want to minimize this fuel consumption. That's the whole point of this specific problem that I worked on. So we have checked some papers and we have used a specific model, and that says actually there are some parameters that directly affects the fuel consumption. So for instance, velocity is pretty much basic, because if you go very fast, you know it spend a lot of fuel on your car. But the other one is called air drag reduction, which is which you can profit for the fact you are very close to one car to another one. So you spend less fuel is because of this air drag reduction. So in short, this plot here shows that how much you can profit when you're doing platooning. So this is the distance. Okay, let's say the cars are 50 meters one away from another. So you have some small benefit, but if they are very, very close to one to another one, you have almost 100% benefit of doing this platooning. Of course, this is zero is too much, but that's the whole point of doing platooning systems, is to benefit from this reduction and try to see this impact on the fuel consumption. Okay. So the other point, as I mentioned before, is like the controllers. That actually the controllers are responsible to keep a certain distance between the cars. Okay, so though I'm not going to go into the details of those equations, but it's just to mention I have considered two very famous on autonomous for cars, for vehicles, called ACC. So in short, the ACC, we have a big distance between the cars when you compare to the CACC, called Cooperative Adaptive Cruise Control. And the difference is that here, because it's cooperative, you have some sort of communications between the cars, some sort of Wi-Fi connection between the cars. And that because of that, you send some information to this guy, and you are able to keep much lower distance comparing to this one. So in short, those are controllers that change the distance between the trucks. Okay. And so what's the point of having those two controllers is that actually we have seen that if this figure pretty much says that if there's no congestion on your traffic. So in front of the platoon, usually there are, of course, traffic, right? There are cars in front of your coordinated cars. So it pretty much says that if there's no traffic in this scenario, one controller has much more benefit in terms of fuel consumption than the other one. And this one says if there are too much traffic in the situation, the other one controller is better. So it shows you have, depending on the traffic situation, one controller can be better than the other one. So the whole question is, okay, how you should change one to the other one. So the whole point is, okay, when you have when you see no traffic, you put one controller. When there's a lot, you put the other one. So that's the whole point of the deep reinforcement learning algorithm in this specific work. So to be more formalized, you have this objective function, which we're trying to minimize, again, the fuel consumption. So all of this is just the fuel consumption. You want to try to improve your fuel consumption for a certain control. You have a control that would keep different distance between the trucks, and those distance you want to know when you're going to switch from one controller or the other one over time. So I have two different options, one controller or the other one. So this is the whole point of the deep reinforcement learning here. So if I come back to this whole agent and environment figure, which is very, very important and common on reinforcement learning, you will see that you have now, for instance, an action that the algorithm can make, which is choose one controller or the other one. And this will impact our simulator, our environment. And our environment is the platoonings. So if you have one controller, the environment will say, okay, the position of the cars are very far away. If you choose the other one, this environment will say, okay, now the cars are very close. So this is the simulator that we used that will change based on this action, okay? And this environment says also, as I said, what are the next, let's say, distance between the cars based on the action. So you need some state. So this is one of the parameters of your state. It's the position of the cars. We have also considered the velocity of the cars, the acceleration and braking of the car signal, and the fuel of each car. So with all of this information and giving some sort of basic reward signal, we know that this agent can solve this specific problem. And for this specific case, we have used a DDKN algorithm. So in short, is a reinforcement learning algorithm with neural networks, as I mentioned, because we actually have infinity possibilities of state space, because the cars can be like a 10.25 meters, 10.2, 10. So depending on how you discretize, you have a bunch of large possibility for your problem. So we have used this neural network, and that's pretty much handles very well discrete actions, because you have just two actions, 0 or 1, which means we have one controller or the other one. So when you use this specific DDKN algorithm, and then, okay, this is now how we model our rewards. So how we are guiding our system. So we have one positive reward for a time, each time step. And if there was a collision, we give some penalty. Okay, I'm not gonna go in the details. There's not much time, but we can discuss this later if you want. But with this specific reward, we were able to, to model our problem. And the other point is the environment, right? We need the environment, which in other words is a simulator. So it means how the cars are moving if you give some sort of action in them. So we have done our own, and now they're open source on GitHub. If you look for this vehicle platoon gym, you will find our specific environment there. So yeah, this is our environment. And those are just basic performance results. It shows, so this is the number of episodes, but it's normalized. But in to be honest, it was around 55,000 episodes. So it means for each episode, in the beginning, the algorithm was very, let's say, dumb. It didn't know anything about, so it was doing some random actions as we saw before. And at some point was learning. So this is actually the average reward accumulated in the final of your step of your episode. So you can see some empirical convergence going up, which means the algorithm is learning how to choose the best switching controllers at each time. So yeah, this is what this graph shows. And this is just quantitative numbers showing that our deep reinforcement learning algorithm, when compared to some classical controller approaches, was better. So it shows that, yeah, it's a very interesting, powerful tool. So very briefly, I will be discussing now a second work, which is related now, as I said, to my postdoc work in the French Institute. And it's called, and it's related to a different type of problem. And also we have used a more realistic simulator. So I didn't create by our own, it was too, this is actually a simulator called Carla, which in my opinion is the state of the art. So the best one, open source simulator for autonomous driving research. Okay, so yeah, it does like some sort of like GTA 5 game. It's somehow very realistic. And the whole point of this work was to use this software, to use this simulator to allow a deep reinforcement learning algorithm go through one point here to another desired point here. And yeah, the car could crash in the building, could crash in another obstacle, in another car that would also add in this simulator. So yeah, you can see there are many possibilities. The car can go wrong direction and so on. So we want to show this feasibility of deep reinforcement learning on this software, on this simulator. So to start with, we decided to take some high-level decision-making action, which it means this specific problem, the action would be, you would have some lateral and longitudinal action, which means the car can go change lane. Okay, you go to this right lane, you could turn right in this intersection, you could go keep on the same lane and turn left on the intersection. So we have some small possibilities to, let's say, put more easily and instead of using so many actions, let's restrict and use less options to the reinforcement learning algorithm so it can converge faster. And the other option would be to longitudinal action. So the car could accelerate, brake, decelerate, or do anything, or keep speed, sorry. So you just keep the same speed as it is. So yeah, we have these option possibilities. So if you do this again, always making this link between reinforcement learning with these MDPs. We have agent, action, environment, state, and reward. What are the links in this work now? The action would be these options to go lateral and longitudinal action. So it could be, for instance, turn right in this intersection, but accelerating. So you go faster, okay? So this is an option, is an action. This would go into this environment. So in this open source simulator that I took on the web, and it's very, very famous in the autonomous driving research. And so this environment will say, okay, if you've done this action, so let's say turn right accelerating, the car will move to some specific position in this simulator, right? So this is the state as t+1. And then what's the state of in our case? So the state would be much more information. Of course, you need not only the position of the car, you need what's the speed of the car, the acceleration of the car. You need to know what are the obstacles, if you can see. So yeah, those are some informations. You know, to know in which lane are you are in this specific simulator. So yeah, you can see it's going, you need more information, right, to give to your agent to take a better decision. Otherwise, just the one position is not enough. And then you have some reward function trying to guide all these agent. Okay, we'll get later in the detail of how this reward function was built. And we have the PPO algorithm in this case, okay, as being the reinforcement learning algorithm. And in this case, this agent called proximal policy optimization is again using neural networks, because we need, we have so many options as in the state space, not necessarily in the action space, because the actions we see, it's just turn right, accelerate, or brake. It's somehow small, but the state space is huge. So you need some state reinforcement learning algorithm, and then we decided to use one more recent in comparison to the other one in the other work. So that's what we use our agent. Then this is how we formulate our state space. So how this algorithm observes the environment. So in this case, we have anyway some ego informations regarding the car that is driving the road, sorry, and obstacles in the road. So you also need, okay, where is this obstacle? What is its distance regarding myself? So you need to take good decisions and better smart decisions. So we have some, yeah, some informations. I'm not gonna go into details of all of those informations, but just to mention, all of this is given to the neural network. So it tries to take a better decision. And it's just to, yeah, for the neural network parameters. And the next one is the action space, which is, again, as I mentioned, it's a discrete. So you have some longitudinal and lateral possibilities. So in the end, we have 0 to 14. So we have 15 possibilities. And yeah, we have, and this is a very interesting, because we try to smaller our options for the to easy the conversions. So then we have how we are gonna guide our reinforcement learning algorithm. So this is called the reward shaping. So yeah, we have some rewards related, for instance, lateral displacement. So it means how far away it's the car from the center of the line, because we consider that the center of the lane, it's the best option to be. Or how is this longitudinal displacement? So yeah, we have modeled some reward functions, and also what we call some sparse functions, which is related to, for instance, if there was some collision in this episode, so we would have some collision reward. So it means, okay, you crash in the car in a building, so yeah, it's very bad, so you have to learn next time it's not good. Or for instance, for the time, it means you spend too much time to solve your problem. So yeah, we have some specific parameters for that. Then finally, I can show some results that shows, for instance, our approach are in orange and in green, and the blue one is the baseline. So it's another paper that also used reinforcement learning in this similar context for this specific simulator that I used as well. And it shows pretty much that on average, we are learning more than this other specific approach on the literature. It shows this is average reward. And we are increasing and learning even more information. So you see on the beginning, you do crazy stuff, and then over time you learn and you're trying to, yeah, maximize your average reward. And finally, I have also some very quick video. So it shows, for instance, in this specific city on the simulator, the car was here and wanted to go to another place. So this is a video that shows that this car is, you can see it moving and turning, it should turn, etc. And in a very good way. I mean, might not be perfect, but it seems reasonable enough for me. So this is some image for the simulator. And again, the car could be stopped, right? On the beginning of the simulator, you see actually dumb actions, and the car is actually stopped for a long time because it needs some iterations and hundreds and thousands of iterations to learn what it should do. I have another one for another, which is considering some obstacles, and it's also doing some predictions. So this reinforcement learning algorithm is accelerating, braking the car based on also on obstacles on the road and avoiding collisions, of course. So those are some, yeah, quick results on this figure. Sorry, with this simulator, as you can see. And so yeah, as you can see, it's very interesting, but of course it's a very tough problem because yeah, when you have realistic simulators as those, to each iteration for your reinforcement learning algorithm takes a long time. Okay, so this is also something very bad on reinforcement learning because you need some sort of loop for thousands and hundreds of times. And this takes some good time because the simulator, it's more, there's this graphic, it's more realistic, so it takes some time, it's time consuming. So you have also some drawbacks, of course, using this approach of reinforcement learning. But I would like to now bring some very briefly current and future deep reinforcement learning applications, also a bit related to automated driving. And the first one is just so far on my presentation, you have seen just simulation application for reinforcement learnings, right? You saw a car moving in a city, going from a point to another one. But how it's actually done on real life? Unfortunately, I cannot speak and share information from my company. So, so of course we are using reinforcement learning in real cars, but I cannot share much information about it. So I brought some real and public and real deployments. So people who really use reinforcement learning algorithm in a real car. So just to mention to guys that yes, it can be used in real situations, but of course it demands time and it's expensive, etc. So this is just I don't know if you guys can see, but it's just yeah, some people on UK, they use the reinforcement learning to make a car learning how to drive. So the guy was leaving this algorithm to learn, and he was stopping the car, of course, to avoid some real collision. So at some point, the car was able to learn how to drive in this specific situation after, I don't know, hundreds of iterations and so on. So yeah, it shows that it's a very interesting way and very it's very nice to see real deployments of this type of problem. But of course you need some simulator, right? So you use some, he created some, they created some simulator for very basic situation that then they would apply in a real car. So this is simulator they do thousands, millions of times, and then in the car was okay, now let's tune some parameters to make this work in a car. And the other one is similar, but was done in, instead of UK, was in Germany. They did the same. They took some simulator for a parking application, and they try to learn this algorithm to park as fast as possible, avoiding collisions in a specific slot. And they did this in a real parking slot in their university, in University of Bremen. So they applied that in a real car. And for instance, this one, they also use the PPO algorithm, the one I have used on my simulations. And just to finalize and to end, I brought also an application for deep reinforcement learning, but not related to automated driving, but relating to the ChatGPT that I think you all knows. This is actually the paper that published the ChatGPT that mentioned and describe how it works. And just to mention that actually one step of the ChatGPT method functionality is actually based on reinforcement learning, and it's based on the PPO algorithm as well. So it shows, yeah, I think we all know how interesting this ChatGPT feature functionality is, and there's also some reinforcement learning application for that. And yeah, just to finish, my last slide is regarding some conclusions about this reinforcement learning for automated driving. And I brought some positive and drawbacks. So the positive points that actually we have some very good generalization capability. So it's good because you are able to cover unseen situations. It means you don't have to, because it makes so much iterations, it sometimes it will be able to see something that we didn't think about it. Otherwise, you have to code, okay, if that happens, you should do this, the car should do that, should do that. So this is actually somehow very interesting to escape, to be able to generalize your solution in many cities, right, around the world. And also the other good thing is because there's optimization for driving policy because of this trial and error. This algorithm can discover optimal strategies that we didn't know, and because of this trial and error facility. But of course, there are some drawbacks, and don't think reinforcement learning can solve your problem. It's everything always depend what you want to solve, what's the type of problems. And one actually very bad for at least for automated driving is this lack of interpretability. It means that actually this algorithm is a bit of a black box because you don't know why it took that decision. Again, reinforcement learning is solving a decision making problem. So you don't know exactly, okay, why this algorithm, in the simulation, it took this action instead of doing that. So you cannot easily prove this. So there's a lot of people trying to overcome this point with reinforcement learning, which are very critical for safety systems, of course, as automated autonomous cars on the road. You cannot put a car on the road that you don't know how to explain why it acts like that. And there's also sample inefficiency because it requires a lot of computing power, as I mentioned before. On the beginning of the simulation, the algorithm doesn't know anything at all, so it's trying to learn. And yeah, it takes a lot of computing power. And there's also this simulation reality gap. So it means to put in a real car, even if you use a realistic simulator, as the one I was using, there are a bunch of problems and limitations when you put you consider a real world application for a car. So I would like to thanks for your attention, and I would have some questions if there is. I guess yeah. Thanks.
Thank you, Dr. Tiago, for sharing your research work with us. And
Yeah.
let me see if there are questions.
Yeah.
Does somebody have a question? Students at the Paraninfo? Okay, we have the questions that we received by chat. First question, how your research of agents down to implementation in vehicles automation are there steps defined to follow for it?
Sorry, could you repeat the question, please?
How your research of
Yeah.
agents down to implementation in vehicles automation are these steps defined?
So how my research, sorry, I didn't understand the question.
Okay, okay. Does the automatic acceleration already cause a kind of undesirable action to the driver?
Okay, yeah. So if I understood well, it's how this action changes the behavior. Well, sorry, I didn't understand very well the question, but maybe there's another question. No.
Okay. If
Maybe I can read also somewhere.
okay, the automatic acceleration cause a kind of undesirable action to the driver.
Sorry, I didn't. Is it Spanish? Maybe you can read in Spanish. I can understand.
Okay, la automatización completa del carro
Sí.
puede causar una acción indeseable al conductor.
Ah, yes. Okay, now I understood. Perfect. That's so good. I speak a bit of Spanish too. Sorry, I didn't understand before.
Sorry.
It's a very no. It's me. I'm a bit nervous too, and I didn't get some part of the question. So, yes, it's a very good point. I think this also question is a bit related to this full automation, where you have you have always some actions that are not desired. It can happen. So the answer is yes. If you have an autonomous cars, and if you're using deep reinforcement learning algorithms, this action can be dangerous, right? Because you can cause some sort of safety problem, like a collision, in your real world application. As you could see, I guess a bit on the video that shows the person was showing his work, how the car it's working. So you see on the beginning, it's about to crash, right? So it's taking some decisions that sometimes it's hard to explain why. So this is why actually today there are no one using directly. They don't have the rights to put a reinforcement learning algorithm in a car and sell this car, because there are a lot of and I'm happy there's a lot of bureaucracy and organizations, political organizations that require and trying to control a little bit this deployment of these algorithms, because of course you need to explain to your client why the algorithm, how it is going to work at some situation. So yes, the answer is yes, it can cause. So that's why it can be dangerous. You need to take caution. And for instance, in all my work, I would like just to, this is very related to the main points of my publication areas. I'm not controlling directly the car so the reinforcement learning in this, the first problem is doing just switching the controllers. So it's not really controlling. The controller are specific control laws. And here the reinforcement learning is the same. It's just doing, okay, try to accelerate and do this, but it doesn't say how. So that's why a lot of researchers like me, we are using deep reinforcement learning, not like on the control part of the car. So yeah, this is very interesting to see.
Thank you. Another question.
Yeah.
Yesterday, Dr. Maite talked about ethical agents, which include a reward for ethical behavior. Having two rewards function, goal, and ethics, it is now being considered in industry.
Wait, sorry. So yesterday there was a presentation about multi-agent systems. That's it. And what's the, sorry, if the question is related, if ethical decisions for the reward. Could you repeat the question, please?
Could be in Spanish.
Yeah, can be Spanish. Let's try, yeah.
Okay. La industria está considerando la ética en la implementación de la automatización de los autos.
It's a very, very good question. Yes, we have to, right? It's something very, very important, and it's something that actually, depending where you want to sell your car or your solution, it changes. So there's actually a very famous work on for the MIT University that they propose people to solve an ethical problem. And this actually, I might be able to MIT social ethical automated driving. So it's very interesting because it's called the moral machine. Is this one? So it's actually one, I could put Spanish, and then you can solve some scenarios that you have to choose between killing people inside the car. So the car is autonomous, and you have to take an action. So the car, either you kill 3 people in this car you are, or you kill like one children and 2 adults. So I don't know, you take some decisions. I'll do like this, and you go on and on and on. So here, for instance, a different one. It says women's, and there are men's here. So who you decide to kill. So actually, the whole thing is regarding ethics behind this study. And in the end, when based where you are answering this, so like you guys are in Mexico, there are people in China trying replying to these questions, and in the end, based where you are in the world, they can see how people prefer, for instance, leaving animals alive than people, or leaving more old people alive than young people. So it is a very interesting work in this topic of ethics. And yes, we have to consider that, because depending where you are in the world, it can be very different. You have to adapt your approach. So yeah, ethics, it's very, very important, and it's being as considering in the company part as well.
Okay, I send you a more question by chat.
Okay.
If you can read.
I will try if I find where. Yes, chat. Okay, is it possible to get the full automation in most of countries, and how long time you think it would be in reality? Okay, it's a very nice question, and to be honest, in my answer, okay, okay, so the question is it possible to get full automation? So here, level 5, in most of countries, and how long time is this gonna take in reality? And my answer is it's gonna take a long time, a long time, a long time, a long time, because this full automation is actually means that the car is able to be driverless everywhere in the world, no matter in Brazil, where I'm from, in Mexico, you guys are, or in India, which is very traffic. And this is impossible for me. I mean, I don't want to say impossible, but it's very, very hard. So I don't think we're gonna arrive at least very soon on this. We're gonna improve a lot and very fast, because we all know technologies, and also with machine learning techniques, everything is going very fast. So yes, for high automation, we're gonna be able. It's not full automation. The difference again is just one phrase. It's this is everywhere in the world. So the car, you put everywhere, like I don't know, in sand or in a mountain, or I don't want to say, of course, not in water, but you put everywhere. It has to be full. It has to be autonomous. So this is very hard. This is like when you put this everywhere. So this is a very different, because this you're saying, okay, you can work pretty much very high automation. So you don't need even a driver, but just in a city or in a country or in a specific place. So yeah, that's my answer for this question. Full automation, no, I don't think we are gonna arrive there. So it's very hard problem. It's that's why airplanes are flying autonomous mode, but not cars yet, because it's very hard. And there are so many more like traffic and anyway obstacles.
Okay, only in the pictures.
Yeah.
Okay,
Exactly.
thank you, Dr. Tiago. The University of La Cañada gives you a
Yes.
digital certificate for your participation. Let me
Thank you.
see.
Yeah. Thank you very much for the invitation. I appreciate again Professor Miguel Sanchez and you for this kind presentation, kind time.